Okay, we're on page 4. We're going to do an example by ourselves now. So I want to show that this for all positive integers is n. Okay, so remembering that for an induction question, we need to follow TAP. So the first thing is to test the base case. And the lowest positive integer is n equal 1. So we're going to test n equal 1. Left-hand side. Now if n equals 1, that's going to end on a 1 cubed. So that's just going to be 1 cubed by itself, which is 1. Right hand side, substituting in, so that'll be a quarter times 1 squared times 1 plus 1 all squared, which is 1 quarter times 1 times 2 squared, which is 4, which is going to be 1, which equals to left hand side. Therefore, true for n equal 1. So that's our base step proven. Now we move on to the next, which is A, which is assume true for n equal to k, where k follows whatever n is, and n are all positive integers, so therefore k must be a positive integer. I like to write k as an element of the positive integers. I like to write like that because it's a bit shorter than writing for some integer k. So what do? I rewrite the original statement, but just change any n's to k. So 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus, that'll be k cubed now, equals to 1 quarter k squared k plus 1 all squared. And I'm going to call that star because we always use our assumption. So TAP, we've done test, assume, now we're going to do prove true for n equal k plus 1. Write down RTP, this is what we're required to prove. Okay, so for the sum, instead of k cubed being the last term, there'll be a k plus 1 cubed. There'll be an extra term in the sum on the left side. And on the right side, wherever there's a k, we're going to put k plus 1. So changing that k to k plus 1, that second bracket there will be k plus 2 all squared. Alright, let's start off with a really long sum, and we're going to use the assumption straight away, and I'm going to use the assumption for this part, okay, because I can replace that by that. So left hand side equals 2, straight away 1 quarter k squared k plus 1 all squared, plus k plus 1 all cubed, from assumption star. Okay. Alright, now looking at what we want to get, I can take out a common factor of a quarter, and I can take out k plus 1 squared, so I'm going to do that. So 1 quarter k plus 1 all squared. Okay, so what's left for the first term is a factor of k squared. What's left for the second term now? If I've factored out 1 quarter, like you can imagine writing it as 4 over 4. You've factored out the quarter. You've still got a 4 here. And because it's k plus 1 cubed, I would still have one factor of k plus 1. Okay, so let's now expand that. K squared plus 4k plus 4. Now that is a perfect square, and that's precisely what we were after. We want it to be k plus 2 all squared, which is precisely what we were after, which equals to the right hand side. Okay, to finish off, we write, therefore, if true for n equal k, then true for n equal k plus 1. And then we write our final conclusion. So therefore, by the principle of mathematical induction, the result is true. And it was for all positive integers n. We've just done our first proof by mathematical induction by ourselves. Alright, let's do another one. Alright, prove that for all positive integers n. So let's go through our tap again. So first step, so because it's for all positive integers n, we need to test the base case, and the base for all the positive integers, the lowest positive integer will be n equal 1. Okay, so the left hand side, convince yourself if n equals 1, that's 1 times 2 times 3, which is the first term there. It'll be 1 times 1 plus 1 times 1 plus 2, or simply 1 times 2 times 3, which equals 6. Right hand side, if you sub in n equal 1, you're going to get 1 quarter, 1 plus 1, 1 plus 2, 1 plus 3, which is going to be a quarter times 2 times 3 times 4. Okay, that cancels and we're left with 6, which equals to left hand side. Therefore, true for n equal 1. So that's my T done, my tap. So now next is A. We're going to assume true for n equal to k, where k matches whatever n is. So k is a positive integer just like n. K is an element of the positive integers. I'm going to write what that is. I'm rewriting the original statement but changing all n's to k. So 1 times 2 times 3 plus 2 times 3 times 4 plus dot 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 plus k times k plus 1 times k plus 2 equals, that'll be k on 4, k plus 1, k plus 2, k plus 3. And I'm going to call that star because we always use that assumption later. So that's the assumed true for n equal k. Now we need to prove true for n equal k plus 1. Write down RTP, required to prove. I'm going to write k plus 1, k plus 2. There'll be one extra term when I get the k plus 1. That's going to change that k to k plus 1. That's going to change that k plus 1 to k plus 2. And that's going to change that if you change k to k plus 1, that's going to change the k plus 3. Equals. Now, this is just going to change all the k's to k plus 1 on 4. That'll be k plus 2. That'll be k plus 3. That'll be k plus 4. Alright. Let's focus on the left-hand side. This bit here is our assumption. So straight away I'm going to use that assumption. So it's equal to k on 4, k plus 1, k plus 2, k plus 3, plus, and then we've got this here, k plus 1, k plus 2, k plus 3, from assumption star. Okay, now looking at this, we can take out, I'm going to write this as 4 over 4, and I'm going to take out the quarter. And I can see common factor of k plus 1, k plus 2, k plus 3, so I'm going to take that out as well. So that's going to be k plus 1 on 4, k plus 2, k plus 3. Okay, what factors do we have left over? So for the first term, we've only got a k. For the second term, it's just a 4. Okay, well, that equals to the right-hand side straight away. So notice, you'll see for these summation questions, we always use the assumption, and then we always, the easiest way to proceed is to factorize. Please don't do the nasty thing of expanding and try and refactorize. Keep everything factored. Always look at what you're trying to get to on the right-hand side. Let's write our conclusion. Therefore, if true for n equal k, then true for n equal k plus 1. Therefore, a final conclusion by the principle of mathematical induction, the result is true. And in this case, it was for all positive integers n. Alright. See you in the next video.